I greet everyone. My name is Roman Sitnik. This is our work with Victoria Gnatushenko, Ukrainian State University of Science and Technology in Dnipro. The title of our work is Integrity Completeness for Supply Chain Data, Trust Model Analysis, and EVM Realization. The paper has three parts. First, we define a security property that we call integrity completeness. Second, we prove which of three trust models satisfies this property and which do not. And third, we implement a model that satisfies it as a set of four smart contracts in Ethereum blockchain, and we measure its cost against standard alternatives. First, as a problem. A modern supply chain consists of many independent companies that exchange data about resources, products, shipments. This data is held in a shared store like a database on, for example, on some backend. And we consider we have an advisory that controls this store. Such an advisory can modify records, for example, quantity, location, timestamps. It can also delete records, and in that case, the event is removed without any trace from the database. In practice, the companies in a supply chain often don't trust each other, and attacks target these boundaries between organizations. The research question is the following: can a verifier detect tampering when it doesn't trust the party that holds the data? There are three established approaches, and each one solves only part of the problem. The first is a database with checksums or hash-based message authentication codes chains. This detects tampering from outside, but the administrator holds the symmetric key, so a malicious administrator can edit a record and compute a new valid hash. The second is per record elliptic curve signatures. Signatures prevent forgery, so a modified record is detected. However, the verifier checks only the records that are still present. If a record is deleted, nothing remains that the verifier could reject. The third approach is the Merkle trees that Ethereum builds at the protocol level of the blockchain. They prove that a transaction is included in a block in the blockchain, but they do not show whether the business data inside the transaction is correct. So, no existing system combines all of this. Application level Merkle trees offer business records together with access control and audit logging in the same transaction. And this leads to the central definition of the paper, the property of integrity completeness. We define it for the verification function V, which reads the store and outputs accept or reject. The definition uses a tampering experiment. The advisory receives the honest store for a dataset D, and it turns into a store for some dataset D prime using the powers of its model. The advisory wins if D prime differs from D by at least one inserted, deleted, modified record, and V still returns accept. The mechanism achieves integrity completeness if the advisory wins only with the negligible probability. Equivalently, V accepts only when the stored data equals the honest dataset. We note that the definition also covers deletion, and deletion is the case that the first two approaches do not detect. We compare three trust models, each under an advisory that controls the store administrator. Model A is a symmetric hashing with hash-based messages authentication code chains. Model B is per record elliptic curve signatures, and Model C is a blockchain with application level Merkle trees on the level of smart contracts. The table summarizes the comparison. All three models detect external tampering, only Model C detects the record deletion, and Model A doesn't detect insider replacement because the administrator can recompute the hashes. Proposition 1 states this formally. Only Model C detects both modification and deletion, so only Model C achieves integrity completeness. The reason is structural, and it doesn't depend on the choice between Merkle trees and signatures. Completeness requires a commitment to the whole set of records stored where the administrator cannot rewrite it. Model B can be expanded, for example, by chaining the signatures or by assigning a Merkle root over all records. but some party must still sign that commitment so that the trust in this network is only moved to another party. So it doesn't resolve this problem. And in Model C, consensus replaces that single trusted party. We now described how Model C is implemented at business level. The tree is built over structured supply chain metadata, not over generic blocks of bytes, like in a simple blockchain. Each event forms a leaf. Equation 1 defines it. The hash of the resource identifier, the location data, the block timestamp, and the center address. Parent nodes are use the standard sorted by rule in equation 2. The hash of the smaller child concatenated with the large one. Building the root takes linear time. Verifying a single record takes logarithmic time, about 14 hashes for 10,000 leaves rather than 10,000. The off-chain implementation in JavaScript reproduces the solidity root byte for byte, so the root can be checked without deploying to a blockchain. The architecture implements the model C as follows. The design goal is that the integrity proof is produced together with the business operation, not as a separate optional step. And the system uses four smart contracts for that. Supply chain core handles the order lifecycle, access control handles the four roles, Merkle verification builds the tree and verifies proofs, and movement manager records the location and ownership history. All four contracts execute inside a single EVM transaction. Under the reverted semantics of the Ethereum virtual machine, if any of the four operations fails, the whole transaction is reverted. And as a result, a state change is committed only together with its integrity proof, its access control check, and its audit entry. And there is no state in which the data is updated but the proof is missing. The separation results identifies model C as a model that satisfies the property. And common concern is the cost of blockchain verification, so we measured it. We measured full dataset verification on synthetic datasets of 1,000, 10,000, and 100,000 records. We compared three systems, SHA only baseline, the blockchain Merkle construction, and the per record evaluated with two independent libraries per record ACDSA. Consider the row for 10,000 records. On-chain Merkle construction takes about 1 second. ACDSA with Node Crypto, which is backed by OpenSSL in C programming language, takes 3 seconds. And so Merkle construction is about 3 times faster. The audited type script library, Noble, takes almost 19 seconds, about 18 times slower than Merkle construction. So in every measure case, full dataset Merkle construction is faster than per record ACDC verification. And this difference follows from the algorithm, not from the Chesov library. Three further results describe how the system behaves. First, scaling. We measure complexity exponent. We measure the complexity exponent lies between 0.99 and 1.05, so the cost grows linearly as expected for hashing. ON hashing. Second, single records proof. Verifying one record costs between 37 and 46,000 gas on chain on Ethereum blockchain and the half a millisecond off chain, even at 100,000 records. This is logarithmic behavior in practice. Third, deployment. We run the same contracts on two public testnets, Ethereum Sepolia and Arbitrum Sepolia. The off-chain times remained within 15% of the local measurements. And the on-chain and off-chain routes matched in every case. And the total gas was almost identical on layer 1 and layer 2. These results confirm that the local benchmarks are representative on public networks. And to conclude, we defined integrity completeness and we proved the separation between three trust models. Only blockchain with application-level Merkle trees in smart contracts achieve this property, and the other two do not. Symmetric hashing doesn't detect insider quantification, and per record signatures do not detect deletion. We implemented this model as a four-contract Ethereum virtual machine architecture, in which access control, business logic, integrity, and audit logging share one atomic transaction. The result has two consequences. The system detects silent record deletions that model A and model B do not detect. And full dataset verification costs less than the record ACDSA. For single record verification, the costs decreases from linear to logarithmic. And for the future works, we will include non-EVM chains not related to Ethereum, such as Stone, Solana, Near, and zero-knowledge proofs for confidential supply chains data. So it's our next route for the research. And thank you for your attention.